Back again to AP Physics with Mr. O'Hagan. Today we're going to talk about work done by gravity. All right. Oh, I already wrote it. Saving some time. Okay, if an object is just falling, so we got some mass, and I like red for my forces. So I got my force gravity pulling it down, and let's say it goes and it drops some distance d. All right. Work done by gravity is pretty easy. Work done by gravity equals the force that's causing the displacement, well, it's the gravity force really, times how far it went. Quite easy. So the work done by gravity equals, force gravity is just mg, and then it's d. Woohoo! All right, so that's work done by gravity if falling. Makes sense. If it's falling, the d, the displacement, and the force of gravity are in the same direction, you got a positive amount of work. So plus if falling. All right, but now if an object's getting shot up into the air, okay, so work done by gravity equals minus mgd if it's going up. All right, so it would be an example of an object going up under the influence of gravity. Oh, I don't know. I just throw a ball up into the air. Let's get up. I don't have a ball. I throw a pencil up into the air. Woo! Look at that. It got bigger. Wow. All right. Anyway, on its way up, the work done by gravity was minus mgd because, well, let's do it. Let's see. So we got the mass, and we've got the force gravity, and of course, on its way up, it's going to move up some type of distance d. All right, the displacement and the force gravity in opposite directions, so you get a minus sign there. So that's the work done by gravity. That's pretty darn easy. Now, let's talk about the work done lifting. It's supposed to say lifting. All right, so if I've got an object here, and I've got a rope on it, which is causing a tension force, I guess maybe I should call it a lift force. All right, so let's just start this again. Here's my object. It's got a mass. There's a rope. So we've got a force lift. What's the other force? The force gravity. All right, so the lift force, if you want to know the work done by the lift force, that's going to be the lift force times how far. And of course, we're going to do one of these where we're lifting it up, so that's d. Okay, easy enough. If our lift force is constant, we can use that. So, give me one of those little arrows. If force lift is constant. All right, that's super easy. Just the lift force, how much you're lifting by times how far it went, that's the work done by lifting. But imagine, if you will, if the lift force is not constant. Non-constant lift force. What do I mean by that? I mean by that, let's say the object's down here, and I will say velocity equals 0 at the bottom, and then here's the path it follows on the way up. It goes, oh, look at this, and we bring it over here, no, and then we do, and then in the end, it's right here, the same mass, and velocity final is 0. There's my initial velocity. And I've lifted it, of course, some distance d again. But we took this crazy path. Sometimes the lift force would be a little bit bigger. Sometimes the lift force would be a little bit smaller, depending upon if we're going around circles or what we're doing. Okay, so lift force will not be constant. But we still have to come up with the work done by the lift. Here we go. How about we try this? Work total equals change in kinetic energy. Work kinetic energy theorem. Yay! One more time. All right. So in our case, what are the two works we have? All right, we're lifting up, so let's just make up the positive direction. So I've got the work done by the lift, that's what I'm going to try and figure out, minus the work done by gravity equals the change in kinetic energy, which is kinetic energy final minus kinetic energy initial. Now remember, for this problem, I made an assumption. I told you the initial velocity was 0, and I said it was a rest at the top, and that's also 0. So if my beginning and final velocities are 0, what happens to the whole right side of this equation? Bye-bye, gone. So work done by lift minus work done by gravity equals 0. So here's what happens. The work done lifting something, if we're at rest in the beginning and at rest at the top, or at the same speed at the top and the bottom, doesn't matter, it has to be 0, all right, is going to equal the work done by gravity. As far as the magnitude goes, the size of it goes. Of course, the actual number is going to be different because the work done by lift is going to be a positive number. The work done by gravity is going to be a negative number. All right, so the actual numbers are one's positive, one negative. But when I get down to here, this is for the size. All right, sizes are equal. All right. Okay, so that's how you handle the work done by lifting an object. If the force is constant, you can go back to the regular work equation. If the force is not constant, because it's some crazy path or whatever, or you're lifting like this, you're like, all right. As long as we have the same velocity at the beginning and at the end, you can use the work. Well, you can always use the work kinetic energy theorem. But if you have the same velocity at the beginning and the end, then that allows you to get rid of the right side. Boom. The amount of joules of work lifting equals the amount of joules of work for gravity. And, oh, this is pretty darn easy to figure out because, we can go back to this. And we can always use this for how big the gravity force is. All right, that's it for work done lifting. I hope you've enjoyed this video. Adios for now.